Okay, so today is a new lecture about UART. You have used UART in your microcontrollers, such as RX and TX, just two lines for serial communication. So if let's don't open it up yet. Just think about it, right? As a designer, for example, we want to write the logic. You don't know the logic yet, but I'm gonna get into the tutorial. You'll see all the state diagrams. But before we get into there, how could we verify the logic we are going to design into the FPGA? So we are going to write a logic module for the FPGA. It's actually making a chip inside the FPGA. It's a UART module, which will have RX and TX, the two pins available from one of the pins on the chip, right? So it's going to communicate with something else. So how can we design the experiment to verify the logic of the UART? Instead of using a microcontroller which has RX and TX, it's going to be the FPGA board which has RX and TX available. Okay, you can imagine that's your Basys3 board, has RX and TX on the board. Okay, how do you verify the logic? Yes, we will simulate it, definitely. How to verify in the real world with any resource we have in the lab? USB to where? So the Basys3 has a USB, and the UART data will be sent through the USB out to somewhere else. If you plug into the computer, yes, it's going to perform as the Arduino board has UART and USB converter in the middle, because you have been doing that to upload your code to FPGA all the time. Okay, so definitely we can use that port to communicate with what? So what's the other terminal of the USB port? That's a computer, right? Okay, so that's one way to do it. Okay, so what about we use one of the GPIO pins available on the board of the FPGA board and assign them as the RX and TX pins for the FPGA. Since it's all flexible, you are doing ASIC design. You can design whichever pin to be used as RX and TX for the chip, right? So if you have that on the GPIO pins as RX and TX, how do you verify that the logic from there? What do you think? What are the ways to do it? It's a standard communication protocol. If it's UART, it's going to be UART everywhere. It's the same logic. Can you connect the RX and TX of the Arduino board to that pin you assigned to be the UART pin of the FPGA and do some data transmission? Yeah. It's going to work as well. Okay. Then how to verify? How to verify if they are communicating correctly? You got two boards. The boards doesn't have any display. Arduino Uno doesn't have anything on it. How do you visualize the results? If you make it complex, you can probably let the Uno board receive the data from the IPGA, right, and then display it on a little LCD display, right? You can send the number over and receive it to a variable and then display it to the LCD. That's one way to do it. Or you can use a soft UART, which is just it's a library you can use, but you don't want to read the drivers for that. The soft UART is being written in C++, and you find another RX and TX pins, and then you use the existing RX and TX from the Uno board through the USB, and so you can send the data to the monitor of the computer. So it's like you have Arduino board, which has, let me draw it so that'll be easier to understand. This is our FPGA board. And you can definitely design a chip and assign the GPIO pins, which is like header pins available on the board, as RX and TX. It's definitely customizable. And then you got Arduino board. So RX and TX, but soft. So it's not a hardware RX and TX. It's something being written in C++. You mimic the logic, looking at the timing diagram and do a time delay and then pull it down and then pull it up. It's just the one and zeros. You can definitely implement it in software. Hardware is something like you have a clock in and the digital circuit will do all the sequence for you as a state diagram, according to the state diagram. But for the soft UART, it's all being written in C or C++ for the microcontroller. So the reason we have to use a soft UART is because the USB port of the UNO board, right? Here's the USB, occupies a hardware RX and TX on the board or the Arduino chip. So you cannot use it for other purposes. So you have to make another soft RX and TX. So we'll have to do it in robotics 2 in the fall. Okay, we'll program a soft, I think, UART probably to do the balancing robot. But now we do the connection here, connect these two. Okay, so the FPGA will be able to send data over to your UNO microcontroller, and then you program it, right? The firmware, whatever, you program it, and then you send the data to here, maybe TX, right? So sending data over to your computer, to your desktop, or the monitor in the Arduino IDE, so you can visualize it. That's another way to debug it. Okay, but so we don't want to make it too complex in this tutorial, so we are getting rid of this intermediate device in the middle. If we just have a FPGA, we just want to practice how to design or implement UART logic into FPGA. Definitely, you need to have a RX and TX port in there. Okay, and the FPGA's RX and TX pins of the chip, right? So here's the FPGA chip, RTX. Forgot how to spell the name of it. RTX or something. 7 X RTX 7, right? So that's an FPGA chip. So they have so many pins. So it has so many pins on it, right? So 2 pins are physically shorted to the RX and TX pins, and then these are physically shorted to the UART to USB converter. It's a little chip on the board. You can see it right behind the USB port. So you have the same chip probably on the UNO board as well. So the UNO board has a USB, and the little black square right after it, that's a UART to USB converter. Okay, so here's a USB port, then to the USB port, right? Here's a USB port. And you can directly connect it to your desktop and open up a monitor. So this monitor is called a serial monitor. Have you used a serial monitor in the past? A lot, right? That's how you debug your Arduino code in there. Okay, serial monitor. So can you use a Arduino IDE serial monitor for this purpose? You're not programming your Arduino board. Is there Arduino involved? No, it's directly just your FPGA and USB. So USB plug into the computer, and then can you use the Arduino's IDE's monitor? So open up the Arduino's programming tool or environment. You open up the serial monitor or plotter, whatever. Can you use it? Why? That's right. Yeah. Yeah, it's just a tool that embedded into the IDE, which will open up the COM port, right? It's nothing else. Okay, definitely you can program in there, but the serial port is a serial port. Serial monitor, it's no difference. So there are also other serial monitors available. They are usually open source. There are many of them. I've used a couple of them. It's just are similar, but there are more functions embedded into the tools. You can select the parity bits or the different body rates. It's just as they're doing the same job. Okay, again, but we are very familiar with the Arduino serial monitor. Why not using it, right? So just open it up and then you can see whatever here being sent to this one. Make sense? Okay, so this is testing. So for this process, right, is testing which functionality of the UART design. You're testing or verifying which part of the UART. Yeah, but which part of the UART? Yeah. TX. Yeah, is that just TX? It's transmission. So this is testing transmission. So how do we test RX? So this IPGA will receive data and do something. How do we do it? Can we use the same serial monitor? Yeah, you can type something in the serial monitor. If you see there's a little box on the top, you can type something into it. But I think since we are trying to test the parity bit, but the Arduino's serial monitor cannot do it, so we are using another open source serial monitor tool. It's available on the tutorial to send something over to your IPGA board. But how do you visualize it? LEDs is a good point. Yes, yeah. So how to do it? Like for example, you type a number 5 in your serial monitor, and then you press send. Okay, so it's going to send through the USB, and then it will be received by IPGA. And then you design the test bench to receive the data and display it to the LED. If it's number 5, then you show a binary number 5 on the LEDs. You can also show it on a 7-segment display. Also works, right? Go to fancier, you can send it over through the VGA and to the monitor. It's just too much as a 1 week tutorial. Make sense? So that's a strategy of verifying the logic, the UART logic on IPGA. So whenever you are following the tutorial on the website, you know the goals instead of just following without knowing why we are doing that. Okay. So I'm going to go through the TX module, and I will either talk about the RX after that, or I'll let you guys understand the RX by yourself because they're very similar. I just don't want to go through too many scripts and code in one lecture. It's super overwhelming, confusing. Okay. So that's a UART protocol. It's very simple. How to get started? Pull it down. So it was high, right? You pull it down, which means you are sending a signal to telling the receiver that I'm going to send something after that logic 0. Got it? Yeah. Okay. And when it's done, okay, I pull it up to signaling the receiver that all the data has been sent. Okay. And I don't know if there are any other types of UART protocols, but for the standard UART, the most traditional UART protocol, it's always 8-bit data. So after 1 byte, it's done. You want to pull it up. So you are signaling the receiver that, okay, 1 byte of data has been sent. Be ready for the next one. Okay, so you can have a parity here, or if you don't want to use a parity, it's okay. But I think the example we have for the RX, we do have a parity bit in there. But for TX example, I don't think we have a parity bit being used. Right? Only 2 lines. RX connect to TX, TX connect to RX. Okay. How do we implement the transmitter? So which is TX. Look at that. So the receiving logic and transmitting logic, they are different blocks, right? That's why for the transmitting, to implement the transmitter, you need module here in Verilog. It's just one digital circuit. It's one block. It's different from the receiving module. So they are totally different individual logic blocks. So now we are looking at the TX. Is there any difference between the TX here and TX here? No, it's just TX for UART, right? No difference. Same logic. So which means if we design or implement the TX logic module in our IPGA, for example, this is IPGA, and we connect it to RX of the Arduino board, okay, even though we don't know who wrote that RX logic for the Arduino chip, but they are going to communicate. That's why we are trying to standardize all these communication protocols, since we know they have the same protocol. If I pull it down, the receiver is going to know that I'm trying to send the 1 byte data right after that logic 0. Okay, so now let's look at the TX protocol. Okay, so there are 3 states in the TX module. 3 states. How many bits do you need to name these 3 states? 2. Okay, 2 bits can do 4, right? I only have 3 here. It's good enough. And at the very beginning, it's so let's look at the circuit first. Okay, so what are the inputs and outputs? That's the TX module. The TX module. Think about why do we need a TX? We need a TX because we are sending a byte to the outside world, right? So where is the byte from? Where we are getting the byte? Is a TX responsible for creating that byte? No, it's from where? From the computer, from the CPU, after the calculation, whatever, right? They just generate that 1 byte. So that's why that 1 byte should be input or output for the UART TX module. Input. So see here, it's an 8-bit data as an input to the TX. And you also need a clock. Since you can imagine you are going to use always add the clock pulse edge to update all the states, right? So you need a clock. And you need a send signal. So the send signal is from somewhere else, from the top, or from this other part of the circuit. The send signal is like a command. Whenever it's ready, send it. The TX module doesn't know when to send it, so you need to receive a command from the CPU. Okay, but we are going to generate that send signal from a different way. You'll know pretty soon. All right, and is that so? The output is sending already. So whenever it's all the 1 byte is already sent, like counting like 1, 2, 3 until number 7, from 0 to 7, it's going to signaling the receiver that the 1 byte is ready. So just sending out the flag. And another output is the data output. So UARTX, which is the data output pin. Should that be 8-bit or 1-bit?
1-bit.
Why? Why not 8-bit? You got 8-bit input, 1-bit output.
I thought the ready was that.
No, the ready is a signal, is a flag.
Oh.
So UARTX is the output of the TX module, which is the data. Should that be 1-bit or 8-bit?
8-bit.
Come on, serial communication. Come on, that's the output. 1 line is 1 bit. Why do you need an 8-bit output for the serial communication? That's parallel, like 8-bit. That's the whole purpose. We need a 1-bit output. Is that 1 bit? It's just 1 line. I pull it down, and after I pull it down, then the next cycle will be whatever is 1 or 0, doesn't matter. See, it can be 0, it can be 1, doesn't matter. It's the data, D0, but just 1 line. Make sense? Why do we need a 1 bit instead of 8 bits? 1 wire is just 8 bits, is taking too many pins, right? It's super annoying. You don't have that many pins on the package, right? Of the chip. So It's a serial communication, which means it's just one line, right? Which means serial. It's not parallel. And you need the clock to pump every single bit out each time. That's why we are doing this. We're taking the efforts here while I'm sitting here lecturing, guys, because we need a 1 bit, right? So parallel in, serial out. Make sense? Don't worry about how do we implement. Don't get overwhelmed. Like, how do we do it? It's all here, right? It shows you how to do it. Okay. So the first state is ready. So ready means it's waiting for the send command. Okay, it's waiting for it. So whenever the send command is just a 1 bit signal or flag, whenever this equals 1, it's which means you can start sending things out. What does that mean? You are sending the parallel data here, like 8 bits, 1 by 1 to here. Just send it out. Whenever you receive the command, send it out. So it loads the bit first and then send it. But actually, it names that. So the name of this state is that send bit. But actually, it loads and sends everything during the load bit state. It's a bit weird, but you'll understand this easily. It's not really complicated. So let's come back to this Verilog code, right? Start with the ready state. It's very simple. Let's start with the first one. Ready, right? Ready, which is the first state. It's waiting. It's waiting. So whenever, so the data, do you know if the data is ready? Is the TX module able to tell if the data is valid or ready or something? Is it responsible or, responsible for telling if the data is good data to be loaded or not? No, whatever is sitting there is going to load it. It can be 0, it can be nothing, right? It can be nothing. So the TX module won't be able to tell anything about the data. It can be nothing. And can be all zeros, can be all ones, whatever. It can be error code. It's going to send it. Okay? Just keep in mind. So whenever the TX module is sending something out, it assumes that the data here is ready to be sent. Right? Okay. First, remember there's a baud rate, which is like 9600 I've been using, right? For the microcontrollers. Okay. So you need to specify that in your Verilog. We are designing the hardware, so you need to definitely define that. But how do you, so why do we need to standardize that baud rate? That's right. That's something like you have to make it work. But down to the bottom level, what's the very bottom level reason or whatever behind the scene? Why do we really need to set up a standard baud rate for serial? Think about that. You have a transmitter and receiver, right? It's keep sending 1 zeros from one side, and the other side is try to receive it. If you don't have the same baud rate, this guy is sending like 9600 bits per second, and this guy is assuming like you are sending like 100,000 bits per second. So it's going to sample at the different spots. You know what I mean? So for example, this is the data being sent by the TX. So the RX knows that here is start. I'm going to delay for a little bit. I know at this point it's going to be a data. And then I do it again, it's going to be a data. Okay, so instead of like data, so I'm assuming the second data, and you are missing all the D's in the middle. So they need to be doing all the things at the same rate, same pace. Okay. Since we know whenever we are connecting our IPGA board with the UART to the desktop, so we want to set it at the exact same rate as whatever you define in your Verilog code. So in that case, when we are sending all the bits to here, what's the frequency should we use? So this is the 8-bit data, right? It's 1 byte, and we want to send bit by bit to here, which is the TX directly connect to the RX. There's no other gates or control logic in between. It's just a wire. Whenever you send it to there, the RX will receive it. It's just one line. So you need to follow a certain frequency, right? So for 9600, the body rate, what's the frequency should we use to send these bits here to this pin? So the RX can receive it at a certain rate. Yeah. So 9600 bits per second, right? So that's the speed we want to use. How do we know that? When you are using second, right? Second is a time unit. How could you find out that standard or time unit in your Verilog? Nanosecond is just for simulation. But physically, what are the resources you can use on the board to find that timestamp? The crystal. What's the frequency of the crystal? 100 megahertz. So that means it's going to oscillate 100 megatimes per second. So now you got a standard, right? How to convert that one to 9600 divided by 9600. How do I understand it? Let's see. It's a middle school level division problem. So we have something oscillating for 100 megatimes per second, okay? And we want to send it every 9600 cuts. Don't know what I mean? Let's try it. So 100 mega, let's do that. Okay, 100 mega counts or pass edges. Okay, let's assume it's 100 mega counts, like 100 mega boom, boom, rising edges per second. Okay, so 9600 counts per second is body rate we are using. So what we're getting from this. So it's just a number of the counts we're going to use, right? So if you count until this number, and then send a bit to the line, then you are getting 9600 counts per second. That makes sense? It's okay, you can take a look at it at the second time after this class. So we are designing a count, which is it's a body timer. It's not really a timer, it's just a count max. So we are counting to a max number like this one. It's 100 mega over 9600. We're counting to that number, then we send one bit to the line, okay? So ready is the first state. Now let's see what we do in the ready state. Ignore this one for now. Timer, reset it. So timer is a count. Wait, is that a timer? What's the timer we're using here? Oh, the timer is a variable, right? The timer is a variable always counting. And this is a counting max. If it reaches this constant, then do something. So the timer is a timer always counting, okay? So reset the timer. And TX bit is actually the intermediate variable which carries the data. It's one bit data being sent one by one to the TX, UART TX, which is directly connected to the RX for the peripherals, for whatever outside the chip. So why do we need a 1 at the very beginning? It's not sending. Why it's not sending? You only have one line. You pull it up. So it's idling, right? It's standby. It's not sending anything. And why? Why you put a 1 there? So you can see that TX bit is 1, right? And this is the within the always block. It's always at, so it's always blocks the case statement until here, end case, okay? And I have another 2 assignment outside of that case statement, which is the TX bit, which is the one we are talking about right now. That one is physically shorted to the output, so there's no logic in between. It's physically shorted to it. So which means if I put a 1 to TX bit, which means I pull that TX line up, which means it's during the standby state. Why? You need to pull it down to start it. So don't start it. Not yet. It's ready. It's waiting. It's waiting. Why is waiting? You are waiting for the send command, right? See this state. Ready is at the very beginning. It's waiting for the send command. If you receive the send command, pull it down. Make sense? Okay. So ready state, I got a 1 for TX bit at the very beginning, so I pull it up. If send is 1, I make up something and then transfer to the next state. So let's don't go to the next state yet. So why do we make up something like this? What is going on for text data here? So what is text data? So what is data? What is data first? Data is the data here, 8-bit. It's a byte. 8-bit in there, right? Okay. So if I'm adding 2 bits, one at the very beginning as LSB and adding 1 as MSB, I'm just adding 2 bits, putting the 1 byte in the middle. So what I'm doing here, why it has to be 10 bits? That's right. Make sense? So the data is in the middle. If you look at the timing, right, you got LSB is being sent at the very beginning, and then MSB is 1, right? So we got a 0 and 1, and in the middle is the data. Make sense? Okay. So you make it up, you get the data and put it into the middle and make up a 10-bit thing, right? And then get into the next state. Okay. First, you see the if statement. See if your timer is up. If timer is up, you want to reset the timer. So what is the timer doing? Counting for what? Yeah. Why we have to do that? What's the frequency? Yeah. What's that? 9600, right? Yeah. So whenever the timer is up, which means it's the time to send 1 bit or 8 bits. Yeah. When it's the time to send 1 bit, I reset the timer. I have to count it again next time, right? So whenever the timer is up, I reset it. I transfer to the send bit state to another state. I'm gonna look into that later. It's a very simple state. And what's going on here? So the text data is the 10-bit data we made up, right? Okay. So the bit index is just the index. It's like from 0 to 9. From 0 to 9. Okay. So we are taking 1 bit each time out and send it to TX bit, which is the physical line shorted to the TX line. The TX bit is shorted to the TX line by this guy, right? It's outside of the case statement. So this block will send 1 or 8 bits to TX bit. 1 bit each time. Whenever the timer is up, send 1 bit and increment the increase that index by 1. Makes sense, right? You move to the next bit until you send all the 10 bits. All right. If the timer is not up, adding 1 to the timer. Makes sense? So send bit It's not actually sending because this one is already sending, right? It's just a name, so you can ignore that. It's okay. So what is this one doing here? When? Yeah, yeah. If you send all the 10 bits, right? Then go back to the ready. Why you have to go back to the ready whenever the 10 bits are sent? You wanna go to the ready for what? To do what? Reset your index, right? That's one thing you want to do. You want to start from the LSB next time. Okay, that's one thing you have to do. And definitely reset the timer, right? Since the 10 bits are read, 10 bits are done, which means actually the 10th bit has been sent, so the timer has to be reset. And you want to pull that line up, right? It's already put up, so just do it again. It's not hurting anything. And then waiting for what? For the send command. So you are in that state. This only state will try to wait for the send command. Okay. So if the send command is 1 again, then just do it again. But otherwise, if the 10 bits are not done yet, then you want to go back to the low bit to keep going until you finish all the 10 bits, right? So that's why it's going back to the low bit. So by default, you want to stay in the ready state. Make sense? Just trying to wait for the send command. So what is this doing here? So what is ready so this variable can get after this statement? This is like state equals ready, then if this equals this, it's returning a 1, right? So if the IPG is in the ready state, then return a 1 to ready, right? So which is the variable, which is one of the outputs here. In addition to that output, the data output. If it's ready, then send a ready, put a 1 here. So what is this connected to? Hmm?
The send line of whatever.
The RX module do not have that ping, right?
Would it be received then?
It's just a signal, right? It's a signal you can use anywhere else. You can use it for any other purposes. But it's definitely not showing up on the outside of the chip. You don't have that pin, do you?
No, but don't you need to send that ready to the next stage to indicate that it's ready to receive?
To the next stage.
Whatever you send transmitting the data to?
For the RX?
Yeah.
Yeah.
On the other one. Like, don't you need that ready state from the TX module to indicate to the RX module that it's ready to receive? Because it's ready to send out?
Inside the same chip or in a different?
Point of
It would
this
just be the
is,
same thing unless
I
you
don't-
wrote it down. Because it would like read a first bit coming in and it's like, okay, that's down, then it'll start receiving.
Yeah.
Same as
It might be used for the RX module in the same chip. Why do we have to do that? I mean, so TX is not doing anything, right? So I think the module here is ready to receive something. So probably doesn't want the two modules running at the same time.
No.
Yeah.
I meant for like
The other module, because you don't have the pin here, right? You don't have the physical pin, do you? It's just 2 lines,
yeah.
right? So actually it's being used for the RX in the same chip. So if you scroll down, you can find it's just a signal, I think. Yep. You can choose to use it, and if you don't have to use it, then just don't use it, right? Okay. So that's the TX module, and how do we use it? How do we verify it? So what we're going to use is a one of the push buttons on the Basys3 board. Think about it. You don't have that board in your mind right now. And you've got a TX module already implemented into the IPGA chip. I got a push button, right? And if you push once of the push button, I'm trying to send a letter through the TX module to the serial monitor on the computer, so I can see a letter A in there. Okay, I push it, I send the A, and I push it again, I send the B, or whatever on the ASCII lookup table, whatever after that A, right? Let's look at it first. So A is what? Oh, character A is here, right? So A is 41, hex number 41, right? So if I press again, press the second time on the push button, I'm going to add a 1 to it. So it's sending a B, sending a 42. So what is 42 in the TX? That's an 8-bit data, right? That's the data. That's whatever data shorted to here. This guy. Okay. So where do you define it? Where do you write the number to here? So this is a TX module, no problem. Done, right? Look at the ports. I got a ready, I got a UART clock send data. So that's just a little module with all the input and outputs, right? Where do you get the A? Where do you get that number for it? You push it. Right now you want to design something which can respond to the push and then convert it into something and then send it to the data line, and so the TX can do the job. So what do you still need to implement this kind of verification idea here?
Module for the button.
Do you need the module for the button?
Well,
So what is a button? Button C, for example, BTNC. That's a physical pin. It's in the constraint file, so you can directly use it. All right?
yeah.
If it gets, I don't know if you're just it would have to be like a logic 1. It's the same as most of the things, I think. You could add to some, maybe 1 byte that you already have, or maybe I'm thinking because you want it set 4, then it started at 2, right? 2 or 1. You just count up from that.
You can assign a constant to a local parameter in Verilog. So just start with for 1. So now we have a TX module, which we just need to design a top module, right? A top module wrap up your TX module, and the top module you can assign a local parameter, can be a constant, like starting with for 1, which is letter A. From there, right, and then connect that one to data or assign it to data. No problem with that. So for push button, you know that it's going to vibrate. So you need a debounce. Have you learned that somewhere else? Debouncing? No? Really? Logic we did a little bit, and microcontroller. Also microcontroller we haven't done that yet, but we push a push button, then use to increase the set point, so the little photo cell have a different set point, so you can track it, right? So it's the same process. You press it for 1 time, you think it's just a very clean logic 1, but actually it's vibrating. It's a mechanical contact. So the mechanical material will vibrate. If you have a high-speed camera, you record it, it's going to be like this instead of a clean contact. No, it won't happen like that. It's a mechanical switch. So you press it, it's going to swing back on and off for several times until it's giving a clean 1. So in that case, the digital system is really fast and smart. So it's going to detect all the swings. Okay, you push it for one time and it oscillates like 10 times sometimes, right? It oscillates 8 times the next time. So, but you want to just define like when you push once, you send one letter instead of push once, send 8 letters, and next time you send 10, right? You just couldn't control. So you need a debounce circuit. Okay, the debounce can be programmed in C++. You're going to do that in microcontrollers. You're going to learn how to do it in C++. It's very simple. But now we are implement a debounce circuit in Verilog. It's going to be synthesized into your FPGA and making a debounce circuit for you. So this is your debounce circuit. It's just a block, right? You got a clock. You got a push button input, which is a button input from the physical button on the FPGA board. That's the input, right? You push it, it's going to send this signal to this digital block. However, after processing this noisy signal, it will be able to provide a clean rising edge. That's what we want. A clean rising edge instead of a noisy signal. Okay? So here's a code to do that. How this works. It has a clock, has a button input. That's a physical input from the, wait, is it? No, it's not yet. It's just the name for this module. It's not a top module yet, right? So this BTN is not the name in the constraint file. You name it whatever you want. It's the button input, and this is a button output. It's a clear button output. And that's a number that we want to count to, and the counter itself, and a variable. So that's just a new button value. If they don't equal to each other, then which means a button is just pressed, right? If you push it, then so can detect the difference. If there's a difference, which means the first rising edge, then start counting, right? But after it rises to the logic high, you assign it back to this parameter just to make them match. So next time it's not getting into here anymore. And if the count equals to delay, because you are always counting, right? It's here, you're always counting up. If this one counts to this number, you can use any other numbers you want as long as it's similar to this range, right? So this is what we want to wait. It'll get clear very soon. It's confusing right now. But so see, if the count equals to 6.5 milliseconds, I'm going to assign X new to the button clear, which is the logic high here. So they are equal, right? When they are not equal, which means you push that button again somewhere else, like a few seconds later, you push it again, so it's gonna get into here again. Okay, so why do we need a time delay here? A very quick comment. When it's gonna get into here during this process for this block, when it's gonna enter this block during this process, since we know it's gonna vibrate, okay, it's for certain it's gonna vibrate, right? So you have this circuit implemented into FPGA. So when it's gonna enter this block during this process here, it's always entering that process because the first time is are not equal because you push it, right? And the second time they becomes not equal because you equalize them within that if statement. So next time it's gonna bounce back to here, so they are not equal again. Make sense? So it's gonna enter this again. So as long as it's oscillating, it's gonna stay in here all the time. Make sense?
Yep.
Okay. So whenever it's not oscillating anymore, it enters else if, right? And you want to wait a little bit. So let's wait I know you are not oscillating anymore, but let's wait. You may oscillate after like 3 milliseconds, but we don't know. Let's wait for 6.5 milliseconds to make sure that you are not oscillating anymore. So which means here, right? You want this one to be at least 6.5 milliseconds in order to claim a clear rising edge. Make sense? Okay. So whenever it reaches 6.5 milliseconds, I just use the new data as a new value here, right? As a Button's value, as a clear value. I'm going to use it, so it's going to be a clean value. So for here, so this pin is going to oscillate, but this won't. Why? Because this only happens here after the time delay. It's not, so btn underscore clear does not participate in any of the activities here. All right, make sense? So we're getting a debounced clean signal from the push button. And now you put them together and design the test bench for it. You got a push button on the board and a 100 megahertz clock as a clock in, and you divide it by 9600 to get that count, right? And send it to the serial monitor. So that's the TX module's verification process. And here's the test bench. I start with a 41. See, it's a 8-bit hex number 41, and every time I push it, I increase it by 1. So this, so that's the button clear, right? That's the output of the debounce module. If this one is 1 and the previous one is 0, which means something has been pushed. So if the button has been pushed, I want to transfer to the send state, which is here. So it's going to send it to the data and add a 1 to it, and then go to a button wait, which is just come back to here. So I have a very quick note for you guys. See this state, this is from the textbook. So all the codes are from the textbook. So see this final state, btn send wait, whatever here, right? I just found out this one is not being used, and you can never enter this state at all, and you don't need it. So you don't have to type it up here, and it's going to work as whatever you expected. It's not going to affect anything. So see here, like you push once, you got A, push, like keep pushing, you're getting all the symbols. However, see what's the body rate I'm using here. Yeah, it's not matching that 9600. Why? Because I think this is trying to teach you that you can override a parameter in the Verilog module. How do you override it? In your top module, right? You included that UARTX module here, no problem. I just invoke it, and then I have this hashtag, right?
Yeah.
Yeah. And what's the name of the symbol? Hashtag.
Yeah.
And parentheses with a new body rate in there, and it's going to override the body rate, the parameter inside that parameter. But you didn't even specify like which parameter you are trying to override. Why is this going to override the exact parameter you want to override? So let's go back to this TX module. Right? As a first parameter here. So if you don't specify it, it's going to override the first parameter. Make sense? It's not overriding this one. It's overriding the first one. Okay. So this will do the job. So it's going to override the first one. And you cannot override a local parameter like this, local param, but you can override a parameter. So if you define a parameter variable, not variable but constant, in here, you can override it in the top module. Okay, so that's how you override it. However, if you have more to override, then you have to do this. Parameter body rate equals this. You have to specify which one you want to override in there. But for this case, you don't have to do that. Okay, you guys need a break, and we will. I'll let you guys go through the RX module herself. It's very similar, and it has a parity bit. And we're going to use a open source serial monitor. It's called Terra Terminal. Okay, and which can, it's RX module, right? So the IPGA board is receiving something from somewhere. So we're using the Terra Terminal to send a bit with a parity bit in there. So you can specify that. Like I'm doing an even parity generator. So it's going to do the job for you, and you are using this body rate, which is the same as the one you're going to use for the RX module. And then you can look at the results on the board, right? So 4 tasks for this tutorial. The first one, use the debounce module to create a counter. Keep in mind, this is something you have to generate by yourself. I don't have a code in here, but I have the debounce circuit provided to you guys. So press the button once, it's going to show a 1 on the 7-segment display. So it's actually have to have a recap on whatever, how the 7-segment display works for the Basys3 board. Make the connection to that. Just keep pushing that, so incrementing the numbers on the display, right, until 9, 25 points. And repeat, no problem. Show the numbers you typed in the serial monitor on the 7-segment display, right, unit. So instead of just doing RX on the LEDs, but also type something here and show it here. So the RX receive it and show it, display it to these units. Less than 10, which means 0 to 9. Make it E there. Any questions for this? Okay, so now let's talk about the RX. Let's have a break. Okay, I'll leave you guys working on all the tasks, okay?